Our mission today is to translate the dense and, frankly, sometimes dry legalese of this specific scope of work into the hidden choreography that brings a megastructure out of the dirt.
I like that phrase, hidden choreography, because that's exactly what it is.
Okay, let's unpack this.
Yeah.
Because the document doesn't just hand over a set of drawings and say, go build it. It forces this incredibly strict taxonomy onto the steel itself. And it starts with mass.
It absolutely does. The contract categorizes structural steel into these really rigid weight classes based on mass per meter.
Right.
They aren't just calling it steel or, even just specifying the grade. They explicitly draw lines in the sand. So light structure steel is anything 20 kilograms per meter or less.
Okay.
Then medium structure steel sits between 20 and 70 kilograms per meter. Heavy structure steel is 70 to 120.
And then there's the big stuff.
Right. Anything over 120 is classified as extra heavy structure steel.
Let me push back on that rigidity for a second, though. Is this basically just an incredibly high-stakes, hyper-detailed IKEA instruction manual?
Well,
Because why segment it that way contractually?
right.
Let's say you have a beam designed at 71 kilograms per meter and another at 69 kilograms per meter.
Okay, yeah.
Contractually, they sit in entirely different categories, right? Heavy versus medium.
Exactly.
Is the physical reality of a 2-kilogram difference really so significant that it demands entirely separate contractual line items and pricing structures?
Yeah, it sounds pedantic, but what's fascinating here is that it's not just about the 2 kilograms. It's about the thresholds of logistics and safety.
How so?
Well, when you cross from medium to heavy, or say heavy to extra heavy, you often trigger entirely different tiers of equipment requirements.
Oh, I see.
That 71-kilogram beam, it might actually exceed the safe working load of the standard site telehandlers, especially when you factor in the boom extension required to place it.
Right, because of the leverage.
Exactly. Suddenly, the contractor is legally obligated to mobilize a larger crawler crane. Rigging charts change. The ground-bearing pressure under the crane outriggers increases.
Which means you need different matting on the ground.
You hit the nail on the head. The contract segments these weight classes because the cost of fighting gravity scales exponentially, not linearly.
That reframes it completely. So the employer is essentially forcing the contractor to price out the escalating cost of gravity up front.
Yeah.
And that prevents those unforeseen equipment mobilization claims later on.
Precisely. If the engineer revises a drawing, which, always happens, and bumps a whole section of a pipe rack from medium to heavy steel, the mechanism to calculate the financial impact is already baked into the contract.
So no arguing over who pays for the bigger crane.
No argument at all. There's no fight over crane rental costs because it's already in the agreed unit rate for that specific weight class.
Which naturally leads to how this heavy metal actually gets manipulated. Because the contract strictly divides the work into a chronological sequence.
3 phases.
Right, through specific work breakdown structure codes. So WBS 300 is phase 1, which is supply, fabrication, and pre-assembly. And the scope here is just massive.
Oh, it's huge.
We're talking carbon steel, stainless steel, storage tanks, vertical vessels, equipment skids, multi-tier pipe racks.
Yeah.
But the detail that stopped me cold was the fabricated shapes.
The plate thickness.
Yes. The contract mandates they handle steel plates ranging from under 6 millimeters to over 200 millimeters thick.
Yeah, a 200-millimeter plate is basically an 8-inch solid slab of steel. Working with that isn't standard fabrication, it's heavy metallurgy.
Right. Explain the mechanics of that. How does a fabricator even roll or shape an 8-inch thick steel plate to build, like a vertical vessel? Imagine you can't just put that in a standard press brake.
You certainly can't. Shaping a plate that thick requires these specialized, heavy-duty plate rolling machines that apply thousands of tons of hydraulic pressure.
Wow.
And often, you can't just cold roll it. The steel has to be uniformly heated to extremely high temperatures.
Like how high?
Sometimes over 900 degrees Celsius.
That is insane.
It is, but you have to do it to temporarily reduce its yield strength and increase its ductility before the rollers can even try to bend it into a cylindrical shape.
Because otherwise it would just crack.
Exactly. And if the temperature gradient is wrong, or if the pressure is uneven, you introduce microfractures into an 8-inch slab, which completely destroys its structural integrity.
And that totally explains why phase 1 is so critical. The contractor isn't doing this in the dirt on site. They are mandated to do this in a specialized fabrication facility.
Right.
But, okay, let me challenge the efficiency of this entire pre-assembly requirement for a second.
Go for it.
Wait, so they are essentially building the building before they build the building?
That's one way to put it, yeah.
I mean, the contract says they had to build these massive 3-tier pipe racks in a shop, potentially dismantle them, or load these colossal modules onto specialized transport, and then reassemble them on site during Phase 2. Isn't that just massive double handling?
It seems like it.
Wouldn't it be way more cost-effective to just ship the raw steel directly to the site and build it once? Kind of like, prepping all your ingredients perfectly in a kitchen before throwing them into the pan.
It sounds counterintuitive to build it twice, sure. But shipping raw steel to the site is just a recipe for massive delays and cost overruns on a project of this scale.
Really? Why?
You have to look at the environment. In a fabrication shop, you have total climate control. You can use automated submerged arc welding machines that run perfect, continuous beads.
Oh, sure.
You have these massive gantry cranes operating on perfectly level concrete floors. If you try to build a complex multi-tier pipe rack from scratch on site wall, your welders are 50 feet in the air.
Hanging off scaffolding.
Exactly. Hanging off scaffolding, fighting wind, rain, humidity. Stick welding and extra heavy beam connection in those conditions drastically increases your defect rate.
Okay. So the employer is essentially mandating pre-assembly as a risk mitigation strategy.
Yes. If we connect this to the bigger picture, you're paying a little more in specialized transport logistics up front to guarantee the quality of the welds and avoid a nightmare of rework on site.
That makes total sense.
Yeah.
So it compresses the site schedule?
It drastically compresses it. Phase 2, which is WBS 301, covering erection and installation, that becomes a highly choreographed assembly process rather than a raw fabrication process.
To just bring the modules in.
Right. Survey the alignment, grout the base plates, and bolt it all together. Then Phase 3, WBS 302 and 303, comes in to apply the roof sheeting, side cladding, and all the weatherproofing.
Which brings up a glaring question for me.
What's that?
If a contractor is executing all 3 of these phases, heavy shop fabrication, complex logistics, and site erection, how on earth do you calculate the billing?
Right.
Because this is where Clause 14 of the FIDIC book comes in, covering measurement and payment. The contract specifies payment is based on measured quantities of completed work,
Correct.
primarily using the metric ton of finished fabricated steel.
The unit rate approach is standard here, and it's heavily reliant on accurate, verifiable measurement. Different elements have different units, too, like gratings and sheeting are measured in square meters, handrails in linear meters.
And stair treads are just counted one by one, right?
Exactly. But the main structure is tonnage.
Getting paid by the ton sounds wild. Why not just a flat fee for the whole bridge?
A lump sum.
Yeah. If I'm the employer spending hundreds of millions on an interconnecting bridge, why would I accept open-ended tonnage risk? Just say, give me a flat fee to build the entire structure.
Yeah.
If you need more steel, contractor, that's your problem.
Because the contractor isn't going to absorb that risk for free.
What do you mean?
If an employer forces a lump sum contract on a highly complex industrial project where designs are, almost guaranteed to evolve, the contractor's estimating team will add a massive risk premium. They might inflate their bid by 20 or 30% just to cover the unknown changes in piping layouts or structural reinforcement that inevitably pop up during the project.
So the employer ends up paying for the risk of extra steel, even if that extra steel is never actually needed.
Exactly. It's a losing game. By using a unit rate per metric ton, you eliminate that risk premium. The employer pays exactly for what is installed.
So if a pipe rack needs to be extended by 10 meters, the contract already dictates the composite rate in euros per ton.
Right, which the contractor has already broken down into material cost, labor cost, and man-hours per unit. It keeps variations clean and fair.
Fair enough. The unit rate makes economic sense. But let's talk about how they actually calculate that weight.
Oh, I know where you're going with this.
Because this leads to my absolute favorite detail in this entire document. The contract explicitly states that when calculating the final tonnage to pay the contractor, deductions shall not be made for standard bolt holes.
Ah, yes. The infamous ghost metal.
You are paying for ghost metal.
Yep.
On a 50,000-ton structural seal project, you have millions upon millions of standard bolt holes drilled into these beams and plates. The contractor physically removes that metal.
It literally becomes steel dust on the shop floor.
Yes.
Yeah.
But they still get paid for the weight of the metal they removed. If I'm an employer's procurement officer, I'm looking at that and seeing tons of missing steel that I'm paying top dollar for. How is that not just huge financial waste?
It looks like waste for sure until you factor in the cost of the alternative.
Which is?
Imagine the administrative burden of calculating the exact volume and mass of every single bolt hole across an entire mega project.
Oh.
You'd have structural engineers and quantity surveyors spending hundreds of billable hours running parametric models just to deduct a fraction of a cent from the bill for each missing tiny cylinder of steel.
I didn't think about that.
The man-hour cost to calculate the deduction would vastly exceed the material value of the steel dust itself. It's an administrative nightmare.
I suppose paying an engineer's hourly rate to count holes is far more expensive than just paying the contractor for the solid beam.
It's an industry-standard pragmatism. You measure the overall envelope of the section, ignore the standard cuts and holes, and just pay the rate.
Okay, but because you are paying by the metric ton, there's an inherent causality here. Paying a contractor based on tonnage incentivizes them to push as much heavy metal through their shop as fast as humanly possible.
Right. Naturally.
The faster they weld, the faster they get paid. So what stops a contractor from rushing the fabrication, producing sloppy, dangerous welds, just to rack up their tonnage billing?
That is the exact tension this contract is designed to manage. And it manages it through an incredibly aggressive web of quality assurance standards and non-destructive testing mandates.
Here's where it gets really interesting.
It really does. The contract ties the physical work to strict international codes. EN 1090 for execution, Eurocode 3 for design, AWS D1.1 for welding, and ISO 19944 for corrosion protection.
And the verification doesn't even start at the welding bay. It starts at the foundry. The scope demands material mill certificates, specifically EN 10204 Type 3.1.
Right. And this raises an important question about accountability. The Type 3.1 certificate is critical because it mandates that the steel's chemical composition and mechanical properties are validated by a testing representative who is completely independent of the manufacturing department.
So they can't grade their own homework.
Exactly. It ensures absolute traceability. If a steel beam arrives at the fabrication shop without that specific paperwork tracing it back to the exact heat batch at the mill, it is rejected. It practically doesn't exist.
So if a weld fails 5 years later, they can trace it back to the exact welder and the exact batch of steel.
To the day.
And once that verified seal is welded, the contractor has to prove the integrity of the joints using non-destructive testing, or NDT.
Which is fascinating in itself.
It is. The contract mandates visual inspection, magnetic particle inspection, ultrasonic testing, and dye penetrant inspection. Let's break down the mechanics of those because it's so cool. We all know what visual inspection is. But how does ultrasonic testing actually find a flaw deep inside a piece of extra heavy steel?
Ultrasonic testing, or UT, relies on the physics of acoustics. A technician sends high-frequency sound waves directly into the steel.
Okay.
Now, in a perfectly uniform solid piece of metal, those sound waves travel at a known constant velocity and bounce back off the opposite wall of the material. But if a welder was rushing and left a microscopic air void or, say, a slag inclusion deep inside the weld joint, that void acts as an acoustic barrier.
Oh. So the sound wave hits the microscopic air pocket and bounces back early.
Precisely. The UT equipment measures the time of flight of those sound waves. An early echo shows up as a spike on the technician's screen, pinpointing the exact depth and size of a flaw that is entirely invisible from the outside.
That is incredible. It's literally like an MRI for heavy metal. And what about dye penetrant inspection?
DPI is used for surface breaking defects that are just too tight for the naked eye to see.
How did that work?
They clean the metal, apply a highly visible liquid dye, and let it sit. The physics of capillary action takes over. The liquid literally pulls itself down to any microscopic cracks. Then, after wiping the surface clean, they apply a developer powder. It acts like a sponge, drawing the dye back out of the crack and highlighting it vividly against the white powder.
It's just like applying an IV contrast dye in a medical scan, but for infrastructure.
Yeah.
And the oversight on this is relentless. The engineer requires a minimum of 5 working days' notice before a hold point inspection.
Right. A hold point is a contractual hard stop.
Meaning they literally can't do anything else.
The contractor cannot proceed. They cannot paint the steel. They cannot ship it. They cannot build on top of it until the engineer has physically reviewed those UT reports, inspected the work, and signed off.
And if we look at the Health, Safety, and Environment section, the HSE rules, they are just as rigid.
Oh, extremely.
Strict permitted work systems for confined spaces and hot work. Lifting plans for cranes. But the detail that really highlights the culture they're trying to enforce is the 24-hour reporting rule for near misses.
Yeah, that's a big one.
Even if absolutely nothing went wrong, no one was hurt, nothing was damaged, if a load merely slips slightly on a crane hook, they have 24 hours to report it to the engineer.
Safety professionals know that a near miss is just an accident where you got lucky.
Exactly.
The contract mandates that reporting because they want to investigate the process failure. Perhaps the rigging chart wasn't followed or the operator was fatigued. They want to correct it before that exact same process failure drops a 120 kilogram per meter beam on a crew the next day.
This rigorous testing, the acoustic waves, the traceability, the near-miss reports, it all builds a picture of absolute, uncompromising control.
It does.
But reading the final sections of the scope of work kind of shatters that illusion of control for me. Because you realize the structural steel contractor doesn't operate in a vacuum.
Yeah.
They're constrained by tight deadlines, and more importantly, by hard boundaries regarding what they do not do.
The interface points. This is where mega projects typically fail.
Exactly. Let's look at the timeline first. Clause 8.3 requires the contractor to submit a highly detailed master program within exactly 28 days of the commencement date.
So they have less than a month.
Less than a month to map out the entire life cycle of drawing schedules, procurement, and identify the critical path for site erection. But then we get to Section 12, exclusions.
It's on print.
The contract explicitly lists what the steel contractor is not responsible for. MEP works, so mechanical, electrical, plumbing are excluded. Fireproofing is excluded, permanent lifting equipment is excluded, but the real shocker is the civil and concrete foundation works.
Completely excluded.
Completely. Wait, so these steel fabricators are building precision towers measured to the millimeter, but they are entirely reliant on the concrete foundation guys doing their job perfectly first.
Including the supply and setting of the anchor bolts, unless it's specifically negotiated into the unit rate.
That is wild to me. That is the ultimate bottleneck.
It is the ultimate baton pass, and it exposes the deeply interdependent ecosystem of the FIDIC Red Book structure.
How do they manage that?
The employer and the engineer have to manage that interface perfectly, because the steel fabricator can do everything right. They can pass every hold point, supply every mill certificate, deliver it on time, but if the civil contractor sets the anchor bolts even slightly out of tolerance, the perfect steel won't fit.
And the site grinds to a halt. The crawler cranes sit idle at massive daily rental rates, and the entire project schedule just hemorrhages time and money.
Yep. And the steel contractor is completely protected by the exclusions clause. They simply point to Section 12 and say, not our scope, not our problem.
So what does this all mean? When you strip away the engineering jargon and the acronyms, you start to see the matrix behind the metal.
Well said.
Next time you're driving past a massive industrial site, looking up at a towering interconnecting bridge or a multi-tier pipe rack, you won't just see structural steel.
You'll see the 28-day schedules.
Right. You'll see the logistics dictated by weight classes. You'll see the ultrasonic technicians searching for microscopic voids. You'll see the ghost metal of 1 million bolt holes that someone pragmatically decided not to count. And most importantly, you'll see the invisible boundary lines drawn between the concrete crews and the steel crews.
Because without the contract mapping out those boundaries and definitions, gravity and entropy would win every single time. The structure only stands because the rules were defined before the steel was ever poured.
Human ingenuity on a scale this massive isn't just found in the physical engineering. It's found in the rigorous, meticulously debated paperwork that governs the risk. We want to leave you with one final thought to ponder, bringing it right back to that critical interface we just discussed.
Oh, the standoff.
The standoff. Imagine this scenario on a remote job site. A heavy transport truck arrives carrying an extra heavy steel column. It was fabricated perfectly. It has its EN 10204 Type 3.1 certificates.
It was tested with ultrasound.
Right. It was paid for by the ton. The crawler crane lifts this colossal multi-million-dollar piece of metal into the air and lowers it down to the concrete foundation. And the anchor bolts, poured a month ago by a completely different civil company, are exactly 1 millimeter out of alignment.
Ouch.
Perfect steel meets the imperfect concrete. Based on everything we've uncovered today about exclusions, hold points, and the strict boundaries of a FID contract, who blinks first in that multi-million-dollar standoff?
See the link in the description for free PDF download. Also, watch our other construction scope videos. Thanks for watching. Please subscribe and see you next time.